All right, so now we're going to learn two new reactions. I'm going to include these together because they should kind of sit in the same place in your brain. They do very similar things with subtle differences, and we'll go over exactly what those differences are. But these are Stille and Suzuki coupling. So these are going to be organometallic reactions that involve a palladium catalyst. Okay, you might see that written as just PD catalyst. You may also see more specifically any one of these three palladium-based things. If you see palladium, you can assume that it works. I don't necessarily need you guys memorizing all the different possible catalysts. That the key sort of thing that should stick out is the presence of palladium in all these. That's going to be the key player here. Okay, so first we're going to tackle these individually, then we'll sort of compare and contrast them. The first one is going to be the Stille coupling reaction. Stille, let's actually use a different color. Stille coupling reaction uses a tin as your metallic ion. And in particular, we call these organostannins. I don't know if it's stannanes or stannins, but I'm going to call them a stannin. Clearly goes for the German word for tin as opposed to the American word. Right? SN, remember, is tin, back from your general chemistry days. Whatever. Point being that that's the metal that's going to be used in these organometallic compounds. And the R, and then we have also an alkyl halide. Okay, so notice again, alkyl halide's kind of playing an outsized role here. Again, first, sort of one of the most important things about these chapters are what are the limitations of these two R groups. R for the organometallic compound can be aryl, vinyl, allylic, or benzylic. Notice that the only thing left off this list are no alkyl groups. The alkyl halide is actually quite restrictive in that it has to be vinyl or aryl, right? So if I'm just going to draw these two out, notice that that means that your halogen has to be attached to an sp2 hybridized carbon. Okay, so the alkyl halide is, so I guess I can't call it an alkyl halide. The halide is actually more restrictive in this particular set of reactions. It has to be a vinyl or an aryl. Okay, and then what happens just as before is you're joining these two R groups, right? So again, one of the things that's powerful about these organometallic reactions is in all of them, you are creating new carbon-carbon bonds. All right, so let's see some specific examples here. So again, the alkyl halide can, the halogen can be chlorine, bromine, or iodine. Actually, iodine is the most reactive. Iodine is also super expensive. So bromine tends to be the go-to, but you will see iodine used at all. It can also be one of these, and this isn't really a halide, a tosylate group. This is basically just another good leaving group. Okay, I'm going to broadly refer to them as halides because it just makes my life easier. But there, you could have this specific leaving group here, a tosylate. Okay. All right, now let's go. How do we predict products? So again, we're going to start out with our organostannin. We got our organometallic with tin here. We have our halide here. So what product is going to be created? Again, we're sort of simply creating a new sigma bond between these two carbons. Okay, so that would mean that our new product would be this here. Predicting products isn't too bad other than the fact you're going to get some big ugly things going on. Similar down here, we're connecting a new bond between the carbon that's at the base of the halogen and the carbon that's at the base of the tin. So here's our new bond here, okay? If we're going to go the reverse direction, how do we figure out what's what? So remember that this can be a little bit more tricky. Let's just review again what our limitations are for the R group that's on our organostannin. This can be aryl, vinyl, allylic, or benzylic. And what about the R group that was on our halogen? This has to be aryl or vinyl. Now, these compounds are color coded, so it kind of cheats here. But if this is my new bond that forms, this has to be originally part of the halide, because this section here does not fall into one of these two categories, right? So this is, again, the considerations of the R group is going to be a very important part of this chapter. So in this case, the halogen would be bound to the benzene ring, and the organostannin would be an allylic organostannin. Likewise, over here, what would this be? Same sort of consideration. This halogen has to be bound to the benzene ring, and the organostannin can be benzylic. Okay. Stille coupling is also stereospecific. So thank goodness if we have a stereochemistry that's associated with either the alkyl halide or, gosh, I'm gonna keep on calling it an alkyl halide. I really shouldn't, because technically this is a vinyl halide. But anyway, the stereochemistry in the halide will be conserved, and the stereochemistry in the organostannin will be conserved as well, right? So if I start off with 2 E double bonds, I'm going to be left with 2 E double bonds in my product. Okay, so that sort of connection is also preserved. There's no funky business going on there. How do we prepare our organostannins? You actually prepare them starting with the Grignard. So that means that sort of another consideration as to the limitations of, I think if I'm being good, yeah, this is the blue R, are going to be the type of limitations that go with the functional groups that are contained on our, any sort of a Grignard, right? So it can't have an alcohol group, it can't have a carboxylic acid group, it can't have any sort of dominatable protons for the blue R. That said, these reactions that take place are incredibly specific. Once you do create your organostannin, they will react very specifically with the alkyl halide, or with the halide portion. So on the halide, you can have a variety of amines, alcohols, ketones, aldehydes. We'll basically say anything on the halide half. Okay. How does this reaction actually sort of occur? Again, we're not really talking about electron pushing mechanism here, but just sort of to go over the 3 steps that are involved in both the Stille and the Suzuki. First, the thing that happens is you have your halide and your palladium catalyst, and notice what's going to happen is that your R group on the halide actually gets loaded on to the palladium. Okay. Now you have your what's called transmetallation. Now you have the R group that's on your organostannin. You're going to mix that with what you've just created. And now notice that both R groups are loaded onto that palladium catalyst. So this is when palladium plays a big role here. The rate at which this occurs depends on the R group. I don't really want you to memorize this sort of list here, other than to note how far down the line alkyl groups are, which is why we say that alkyl groups do not react cannot be the blue R, cannot be the organostannin compound in the Stille coupling reactions, right? So we said it could be vinyl, aryl, allylic, or benzylic. It cannot be alkyl. And that's just because this process here is way, way, way too slow with an alkyl group. And then the last step is kicking off both of these R groups from the palladium catalyst in such a way that now they're both bound together, right? So this R group was on my palladium catalyst. This R group was on my palladium catalyst. That gets kicked off in such a way that now they're bound together. And importantly, because it's a catalyst, I've regenerated that palladium catalyst. Okay, so just sort of I think this chart probably will scare people a little bit, but it's really not that bad. It's just illustrating those 3 steps. So first, starting off, you have the catalyst all by itself. The first step, it would be the oxidative addition, where you've loaded the R group from the alkyl halide on there. Then you have transmetallation, such that both R groups are loaded on there. And then third, you're kicking off those 2 R groups in such a way that they're bound to one another, and you've regenerated your catalyst. All right, so now let's move on to the Suzuki coupling. Notice again, we have that same list of palladium catalysts that can be used. Okay, so again, the key thing that I want to jump out into your mind is when you see palladium, you're thinking either Stille or Suzuki coupling. Okay, and again, there's a lot of overlap between these 2 reactions. That's why we're sort of combining them into one lecture. At the very end, we'll really sort of summarize what the distinctions are. Okay, actually, the first one you can see, well, the thing that really makes a Suzuki, let me just use a different color, is that we're talking about using a different organometallic compound here. It's not an organostannin, it doesn't involve tin, it's an organoborane. So boron is the key player in this Suzuki coupling reaction. And you can sort of use a few different borons. There's methyl groups, ester groups, acid groups. It doesn't, I don't know. Really, if you said RB, R2 or something, I guess you don't want to say the R twice. Let's say R prime, BR2, whatever. This is a perfectly suitable Suzuki organometallic sort of thing. You don't have to specify one of, yeah, we'll see a few. You want to be able to sight recognize some of the ones that are commonly used. But in terms of like what I would be looking for on an exam, if you had to list reagents, you can just put like generic R group, or you can use Y if you would prefer, just like they did here. Okay, so now we can actually see our first distinction of the Suzuki with the Stille by looking at the different, what the different R groups could be. So first of all, I just want to note that your halide, the R group there is the exact same limitations for the Suzuki and the Stille coupling. Still limited to aryl or vinyl R groups. The halogen has to be bound to an sp2 hybridized carbon. Okay, so you can just put those together in your mind. Suzuki and Stille, the halides that are used have the same limitations. Turning to the organometallic compound here, the R group that can be attached to that metal can be aryl, vinyl, allylic, benzylic. Plus, for the Suzuki, you can also use alkyl groups. Okay, so this is our first distinction. The organometallic compound, in this case, it's an organoborane, can have just the same groups as it does with a Stille plus the alkyl. Okay, and so this can be, R can basically be anything for a Suzuki reaction, right? Aryl, vinyl, allylic, benzylic, alkyl, that kind of covers all the bases. So how do we prepare our organoboron compounds? So I guess let's look down at the bottom here first. First would be similar to the Stille reactions, which were prepared from a Grignard. We can prepare our organoborane compounds from an organolithium, right? So starting out with some way stronger organometallic compound and then tossing in boron, we can be left with one of those organoboron compounds. The other way that we can do it is actually, I don't know if flexible is the right word, whatever, less restrictive. We don't have to start with another organometallic compound. We can actually just start with a pi bond, and the boron will react with that, forming these reactions here. These, again, I don't really need you to memorize structures or anything like that, but I do want to point out these here are the most popular ACS organoboron compounds to use. Okay, so you may see those structures on the ACS. BBN is this weird looking bicyclic compound with a boron. Kate-Call borane, whatever, however you say that, where you have this ester boron bound to this ester that's bound to the benzene ring. These are the two most popular ones that you might see. I don't really care if you memorize these structures for my exam, but I do want you to be able to sight recognize them as something that would be involved in a Suzuki reaction if I gave you them in a question, right? So again, not something that I would expect you to regurgitate from memory, but if you see it down, you know, oh, okay, Suzuki. Okay, that's an unimportant thing here. Okay. But anyway, it could just react with the pi bond. Notice that then it breaks that pi bond. So here, if I'm keeping track of carbons, this carbon that was on the tip there is now what's going to be attached to my boron. Okay, so predicting products, again, kind of not that bad. If I'm giving you reactants, it's not too hard to go to products. Oftentimes the reverse route direction is harder because then you have to consider the various limitations, but you're just going to look what's at the base of my organoborane. That carbon is going to be bound to the base of whatever the halogen is. Notice here it uses that fancy tosylate leaving group. But those are going to be the two carbons that are now bound together in my product. Okay, same thing over here, right? So the base of that halide is now going to be bound to whatever that boron is attached to. That's how sort of easy it is to predict products for these reactions. Okay, notice that in terms of reagents that's used, again, the key thing, let's use a different color. The key thing that you should see is palladium, and that has you thinking this Stille Suzuki coupling direction. May just say palladium catalyst. It may give you palladium with something ugly on the back end. Whatever it is, the palladium's the thing you notice that says, oh, okay, I'm on the right path here. And then in addition for the Suzuki, we have this base that's going to be used as well, strong base that's going to be used. So keep that in mind. Okay, so in terms of comparing the two, there's a ton of overlap between the two. Most things that you can do with Stille coupling, you could do with Suzuki coupling and vice versa. The biggest thing that we've seen up until this point is Suzuki coupling can also use just straight chain alkyl groups. Okay, so this is just a good summary of things that you can do both with, or things that you can only use Suzuki coupling. Suzuki is considered sort of like more flexible. The other thing that's really important is that Suzuki is cheaper and less toxic, right? Anytime something is less toxic, it implies cheaper. But anyways, the cost of the materials, which is of course not a really big consideration when you're doing pencil and paper organic chemistry, but if you're running an organic chemistry lab, that's going to be a huge consideration. Again, just like the Stille coupling, Suzuki coupling reactions preserve stereochemistry, both in your organometallic compound and in your halogen. So I don't know, I think that's best case scenario. You don't have to worry about any sort of weird rearrangement or anything like that going on. Disadvantages of Suzuki though, is that it requires that strong base, which means it's not going to be compatible with any sort of acidic proton. And this actually includes ketones or aldehydes. So we do not think of ketones as aldehydes, ketones and aldehydes as having readily donatable protons. But because of these conditions of these reactions, those alpha protons that act like acid, sometimes they can be plucked off, and then you have these side aldol type condensations. So anyways, you have a same sort of reaction wheel that goes down with the Suzuki reaction. We don't need to spend too much time on that. The bottom line is you have your palladium catalyst, you have the R group from the halogen that gets loaded on. This is actually the step where the base becomes important, and it makes it easier for the R group from the organoboron compound to hop on. And then those both get kicked off in such a way that they're bound to one another, and we regenerate our catalyst. Okay, so just to summarize here, these slides are going to be great for when you're doing your review. We know how to prepare our organostannin for the Stille coupling. We then have the coupling reaction and importantly, the limitations on those R groups. And then this next thing here just demonstrates how we preserve our stereochemistry, or that are stereospecific. Same thing with the Suzuki. We know how to prepare these reactions. Actually, notice here they gave you now a new one here. Again, it's the pi bond that's reacting. So if we start out with an alkyne, then what we'll get at the end is a vinyl organoboron compound. If we start out with an alkene, then we get an alkyl. And we can always also just start out with an organolithium compound, react that with boron in order to get our organoborane. And then again, sort of the limitations on the Suzuki reaction. The R limitations are the exact same as the Stille, aryl or vinyl. The big difference is in the organometallic portion and the fact that you can actually have an alkyl group attached to the boron in addition to aryl, vinyl, allylic, benzylic, which were the same as the Stille reactions. Okay, so now just to summarize real quick, again, in terms of R, in this case R prime, aryl or vinyl. That's the same for both the Suzuki and the Stille reactions. So this slide is really a summary of the differences here. One of the big ones being the limitations of your organometallic compound. In the Stille, you use tin, and you can only have aryl, vinyl, allylic, or benzylic R groups, no alkyl groups. Whereas for Suzuki coupling, when you're using boron, you can have aryl, vinyl, allylic, benzylic, or alkyl groups. Okay. The organostannins are prepared for Grignards. So there's all the limitations of what other functional groups can be on the organostannin based on like, it has to be compatible with a Grignard. Suzuki is actually preferable in the sense that it is cheaper and less toxic. So when would you ever use Stille coupling over Suzuki coupling? Key thing here being that there's no limitations on the functional group of the halide for Stille coupling, whereas when it's Suzuki coupling, you can't have any acidic protons, and this includes ketones and aldehydes, which again, we don't really consider to be acidic protons in most settings, but bottom line is in these Suzuki reactions, if you had a ketone or an aldehyde, you would end up having side reactions of aldol addition and condensation. Okay, so that's really the limitation of when you would use Stille over Suzuki is when you have these other functional groups that are incompatible with the Suzuki reaction.